Okay, this is section 6.2, the binomial distribution, and this is a very involved section. There's a lot to do here. I mean, the previous sections have been a little bit challenging as well, but what makes this section a little bit difficult is there's some calculations, there's a lot of spreadsheet work that of course you could do by hand, but it's much easier done via spreadsheet. Like we've done in the past, but you're gonna have to pay really close attention when we get to it on all these calculations over here. I just split the screen right away so that we could kind of just work and not bounce around everywhere. But this initial part, what you're gonna do is you're gonna need to reference your notes. Your notes are gonna help you quite a bit in answering these initial questions. And then towards the end of this section, we're going to move very heavily into work on the spreadsheet, the right side of that screen. Okay, let's take a look. A binomial experiment is performed a fixed number of times. What is each repetition of the experiment called? So if you look at your notes, that is known as a trial. So each repetition of a binomial experiment is known as a trial, or is called a trial. Okay? All right. Determine if the following statement is true or false. In the binomial probability distribution function NCX. Now this is before we have seen maybe an NCR where we're doing combinations. This is very similar. It is the combinations formula where R is changed to an X, and we'll see that used quite a bit. You can already kind of see it over here that we're going to reference that. It is calculated in the same way that we did before, n factorial over n minus r factorial times r factorial. So just like before, we know that NCX is n factorial over n minus r factorial, but in this case, your r's are actually going to be your x values. So if I rewrote that, it would be n factorial over n minus x factorial, or times x factorial. So it's the same thing that we had done in the past. So the only difference is that we now call it NCX. So it is the combinations formula as we've seen before. So let's take a look here. In the binomial distribution function NCX represents the number of ways of obtaining x successes in n trials. And that is true. So again, this is in your notes as well. NCX is the number of ways to obtain x successes in n trials. In other words, if I had n trials of something, if I tried, let's say for example, to do something 10 times, x would be the number of ways that I could get it successful. So another thing to note is that in a binomial distribution, and we'll see more of this later, there are certain characteristics of it, and the characteristic is that it's basically on-off, two mutually exclusive outcomes. In this case, it would be a success versus a failure. It's binomial, there's a duality to it, okay? All right, number 3, what is the formula for the expected number of successes in a binomial experiment with n trials and probability of success P? So the letter P, of course, is used to denote probability, as we've seen before. So when you see the letter or the variable P used in our problem, so P, you see P all through here, and these are answer choices. You see P used over here, P used through here. So whenever you see P, that is short for the probability that is provided for you, or you need to calculate on your own. So what is the formula for the expected number of successes in a binomial experiment with n trials and the probability of success being P? Well, you can either look at your notes or research it, but the bottom line is that we've seen this before. We've seen it before in the past. All you have to do is multiply your n number of trials by your P probability of success. So it is straightforward. There it is, the expected, E for expected number of successes. Okay? Now, one thing to also note, and it's in your notes, is that your expected number of successes in a binomial experiment, this is also known as your mean, okay? So when we get to it, you can clearly see over where, well, it'll be down lower, but You'll see later on, we're going to get to it, n times p is the mean. I'll reference that later. So I'm kind of referring to these things now to kind of plant some seeds for you so that when we move over to the spreadsheet, it doesn't look completely foreign, but it will be a little bit of a leap to get there, okay? So we'll just kind of work our way over there. Let's take a look. Next one. Determine if the following probability experiment represents a binomial experiment. Okay, so if you look in your notes, there's a category here that characterizes or describes or lists the traits of a binomial experiment. There are many traits below that. It begins with discrete variable, 2 mutually exclusive outcomes, trials of the experiment are independent, probability of success is the same from trial to trial, experiment performed a fixed number of times, and gives you a couple examples. That's all in your notes. So let's take a look at this and reference that part of our notes. A random sample of 15 professional athletes is obtained, and the individuals selected are asked to state their heights. So the question is, okay, here is a scenario, here's an experiment, and they want to know, does this fit the criteria for a binomial experiment? Does it check off all, and it has to fit all the criteria that are listed in your notes? Does it do that? Well, if you can find simply one criteria that it fails at, then it is not going to be a binomial experiment. It has to satisfy all of those criteria. So with that said, the first thing is random sample. That's good. That means that all of our athletes are going, all of our athletes in this case are going to be independent. Okay, they're not going to be related. That's great. They're mutual, and so the next thing is the individuals selected are asked to state their heights. Okay, this is a problem because heights are they change. There's not an outcome to that. There's literally, you got a big wide range. What you have to do is think back to the previous problem that we saw of success or failure. That's the kind of outcome that you're looking for, okay? Are they above 5'4" or below 5'4"? Are they above 6 feet or below 6 feet? That is more in line with being 2 mutually exclusive outcomes. Just stating their heights is not related to that. So this is not a binomial experiment. And so let's find the reasons. So D looks like it's the best one. Let's take a look. No, this probability experiment does not represent binomial because the variable is continuous and there are not 2 mutually exclusive outcomes. That's it right there. So the variable is continuous. Our understanding of continuous variables from earlier states that you could get all different answers essentially and in between your whole numbers. And that's part of it, but the other part is that there are not 2 mutually exclusive outcomes like success or failure, okay? So there it is. All right, let's take a look at number 5. An experimental drug is administered to 40 randomly selected individuals with the number of individuals responding favorably recorded. Okay, so an experimental drug is administered, okay, to 40 random selected individuals. That's looking great right now. That means that none of these people are tied together. They're independent of each other. So that's a great start. The number of individuals responding favorably recorded. I like that because the key word is favorably. That means that it's like a yes or no, favor, unfavor. It has a duality. It can be a sort of, it meets all the criteria of the binomial. So I'm going to say that it is, and it seems to satisfy all the criteria, and that's correct, okay? So if you look at the no's, they actually contradict that. So no, because the trials of the experiment are not independent. Well, they are independent. Each person would not be connected to the other in terms of their results from the experimental drug. No, because the probability of success differs from trial to trial. Not really, because what happens here is that that probability of success supposedly should be the same. So every single time somebody gets the experimental drug, there is a reset on it. So, and as a result, we should have the same general probability for every person in general or the trial. No, because there are more than 2 mutually exclusive outcomes for each trial. No, that's not true at all. there is. There's only two mutually exclusive outcomes, favor or unfavorably, okay? All right, number 6, determine whether the following, same thing, okay? 4 cards are selected from a standard 52 card deck without replacement. The number of kings selected is recorded. Okay, so let's take a look at this, and for this problem, let's just go through each of the options. So we'll approach it a little bit differently, but we're still going to do the same thing. Let's look at option A. It's not because the experiment is not performed a fixed number of times. Well, it is a fixed number of times, 4 times, the cards. So that's not the reason why. Yes, because the experiment satisfies all the criteria for a binomial experiment. Well, I'm going to tell you right away that it's not. All the criteria are not satisfied, and hopefully in these next 2 C and D options, we're going to see why. But the key word here is without replacement. And if you understand your previous section's homework, previous things that we've done prior to this section during the course of the semester, you know that the phrase without replacement means that whatever I draw on one hand or one of my cards, if I don't replace it, that means that the next card is its probability or its outcome is going to have a tie, or is going to be tied to, related to, connected to, dependent on, and that's the phrase here, the previous one. So that's a problem, because based on our criteria, binomial experiments, the trials of the experiment have to be independent. These trials cannot be independent because when I pull one card and I don't put it back, I'm not resetting the deck and starting fresh. That would be independent. But now, because I take out a card and then I leave it out, I'm now dependent. Okay, so let's take a look at C. So clearly this is not a binomial experiment. C, no, because there are more than 2 mutually exclusive outcomes for each trial. No. Well, let's take a look at the last one, and then we'll look at it. No, because the trials of the experiment are not independent and the probability of success differs from trial to trial. That's the answer, but let's talk about C. No, because there are more than 2 mutually exclusive outcomes for each trial. Well, that's not really the case here. I mean, that's not even kind of like in line, because 2 mutually exclusive outcomes is kind of like, that could sort of be it, but I mean, the better option is going to be they're not independent, and the probability is going to change, okay? All right, number 7, a baseball pitcher who strikes out 25% of her batters is asked to throw pitches until she strikes out a batter. The number of pitches attempted is recorded. Now remember, you want to have kind of like all of these criteria satisfied, so they have to be satisfied. Let's take a look at our options. No, because the trials of the experiment are not independent and the probability of success differs from trial to trial. I don't know, because here's the deal. Every time the pitcher throws a ball, we're starting a whole new throw, a whole new opportunity for the batter. So I would say that the trials are independent. I mean, you don't want to, you're not taking the mental component into it, and so I guess from a mental standpoint, technically, one trial falls, can impact the next because maybe the batter is shaken up by the previous mess up or strikeout. But I don't think they're really going that deep into it. What they're really trying to do is get you to understand that, look, every time the pitcher throws a new ball, it's a whole new ball, literally. So that would mean that the trials, every pitch, from trial to trial, pitch to pitch, is indeed independent. So I don't think A is the right answer. No, because there are more than 2 mutually exclusive outcomes for each trial. That's not the case. You either hit the ball or you strike out. So I think that this is probably okay. I think that we do have 2 mutually exclusive outcomes. You either hit the ball or you strike out. So I think that's okay. Yes, because the experiment satisfies all the criteria for a binomial experiment. I don't think so, and I'm going to tell you why, and that's D. No, because the experiment is not performed a fixed number of times. This is the right answer. This is the right answer, and if you look at your criteria or characteristics for a binomial experiment, you will see that the last one says the experiment must be performed a fixed number of times. This one does not meet that criteria. While it does meet some other criteria, it does not meet that last one because the pitcher's going to throw pitches until the batter strikes out. So there's not a fixed number of, okay, you're going to throw 15 times or 10 times and so on and measure it. So I think that's the right answer, and it is. Okay? All right. Okay. Number 8, an investor randomly purchases 9 stocks listed on a stock exchange. Historically, the probability that a stock listed on the exchange will increase in value over the course of the year is 46%. The number of stocks that increase in value is recorded. Okay, let's take a look here. So, well, if you look at your examples, this actually is one of them that's in there. But let's go through it. So it is a yes. So I mean, you can either ignore it, but we could go through each of the options. No, because there are more than 2 mutually exclusive outcomes for each trial. No, because you either increase in value or you don't. Up or down. Increase, don't increase. So there are 2 mutually exclusive outcomes. No, because the probability of success differs from trial to trial. This is not true because 9 stocks generally 9 stocks represent 9 different companies, which means that they are independent of each other in general, unless these companies are tied together in some way, but we're going to assume that they're not. And so 9 stocks means 9 different companies, which means 9 different outcomes, which means, or 9 different trials. So the probability is going to, it's not going to change from company to company. No, because the trials for the experiment are not independent. They are independent. They are independent. So I do think that is why C is the correct answer. Okay? All right, so that takes care of the basic understanding of binomial, the binomial distribution and binomial experiments. Now we get to the actual calculation, okay? And I refer to some of the things on the right-hand side of the board in the Excel spreadsheet that I created. I'm not going to send this to you because I want you to create it for yourself. That's part of the learning process. If I sent this whole spreadsheet to you, then it takes some of the learning out. So pay close attention, and of course you can pause this video and take those notes and look at the cells. But you really want to kind of understand this. Let's take a look. All right, so here we go. We've got a binomial probability experiment is conducted with the given parameters. Compute the probability of X successes in the N independent trials of the experiment. Okay, so we have an N value, a P value, and an X value. So if you look in your notes, there's a formula, and the formula says in order to calculate the probability, okay, the probability of some X, you need to first obtain NCX. Then, after that, you're going to need to take the probability that's given to you and raise it to that X power. Then, you're going to need to take 1 minus the probability, okay, and raise that to the N value minus X. Okay, and that is your formula. Okay, so that's in your notes, and I actually should change this from max to N. I don't know why I put a max there, but I'll do N minus X, and that's going to come down here as well. All right, so there we go. Good. Okay, so with that said, each of these will be multiplied, and you can see that in my formula over here, I have NCX, the probability to the power of X, 1 minus the probability to the power of n minus x, and then the product of these three things is this value right here. So I'm getting you familiar with doing the calculation. So with that said, what I want to do is calculate this problem. We are now going, now that we know the formula, which is in your notes, where is it in your notes? It's right above the note that says binomial experiment. So that area that we've been talking about earlier with respect to binomial experiment, right above that is the formula for P of x. All right, so how do we calculate P of x? Well, let's first do this part right here, item number 1, NCX. So in other words, the combinations formula, and you could do it on your calculator. You could go to that website that I gave you the link for. There's a lot of ways to do it. What I did is I saved some time, and what I did is I just created a little Excel calculation for that. If you want to see that, as you can clearly see here, I put an N area, an X area, and an NCX, and notice there's my formula for calculating NCX, okay? And essentially, when you go to, and you can see it up here, if this is in the way, it's right here as well. You can go to that website, and essentially that website is doing something very, very similar to that. And what does fact stand for? Factorial, factorial. So I'm taking the factorial of this value, dividing it by the factorial of the difference between these two values, and multiplying it by the factorial of my x value right here. And so that's how I just created an easy little calculation for myself in Excel. But of course, you don't have to do that. If you got it on your calculator, you can have your calculator do that. No big deal, real easy. Pull it up on that website, have it do it manually. It's really up to you. It doesn't really make a difference, okay? So what is the very first thing we need to do? We need to calculate NCX. Well, I know for mine, here's my N, and here's my X, and my marker's all out of ink. Let me get another one. I'm gonna have to go with some blue. All right, so the very first thing I do is I need to calculate NCX, and so there's my N, there's my X. All right, so what does that look like? Well, how about I actually write it out? That's going to be what? 12N, the combinations formula, C, and X. You will not use the permutations formula at all in this section. It's always the combinations formula. So over here, I'm going to come over to my spreadsheet. You would be either, you can make it up your own on your spreadsheet, or alternatively, you could simply do it on your calculator or the website. So that becomes 66, or that is 66, not becomes. So 12C2 is 66. There are 66 ways of having 2 successes out of the 12, okay? All right, with that said, what's the next thing we need to calculate? The probability to the x. Now, another way, and I do want to show you guys this, I'm going to come up here and I'm going to show you this part over here. And actually, I'll deal with that later, okay? No worries. So let's do this part over here, okay? So what is the probability? The p right here is the 0.4. So 0.4 to the power of x. What was my x value? Not 12, 2. So my x value was 2. So what I have here in my second step is I have to raise 0.4 to the power of 2. So I'm just going to do this off to the side here to save myself some time. 0.4 to the power of 2. You would do it in your calculator. That's 0.16. I mean, anybody could have done that probably in their head, but I just want to show you well, I guess you can't see it. But anyways, it's not really that tough. You can do it on a calculator, you can do it in your head. This one's easy, it's up to you, okay? How you want to calculate it. All right, let's do the last part. The last part tells you to do what? 1 minus the probability, 0.4, And then what you're going to do is take your n value, minus 12, yours is probably different, and subtract from it the x value, 2. And there is that piece. So what is that? That's going to be 1 minus 0.4 is 0.6. 12 minus 2 is 10. So what I've got to do here is I need to calculate, this is really 0.6 to the power of 10. So I don't know what that is, but I'll just do it over here. 0.6 to the power of 10. There it is. It's 0.00 blah, blah, blah. Okay? So I'll write that down. Let's see here. 006046618. And I just missed that. 6046618. Okay. All right. There are my 3 pieces that will help me calculate the probability of getting 2 successes in n independent trials of the experiment, given that the probability of a success is 0.4 on each trial. Okay, so I'm going to save some time, take a look at what I'm going to do here. My answer is going to be, what, 66 times 0.16 times that 0.00604. You can calculate that on your own. What do I end up getting? I got to round to 4 decimal places, 0.60639. So 0.0639 should be my answer. Okay? Let's hope that that's right. If not, we're going to have to go back and check our work. 0.0639. And it's good. All right? So this is really, really important because we are going to be running these calculations for the next 5 problems. 4 or 5 problems, okay? And so this is kind of like what's going on in the background. What I'm going to do is I'm going to automate it a little bit so that we don't have to do this hard calculation over and over and over again. We can save our time and you don't have to work so hard because the calculations are very, very tedious for the problems that are, for the upcoming problems. This is what I would consider an easy one, okay? So there it is. That is how you calculate the probability P, okay? So if they give you that and they're asking you to calculate the probability, there you go, okay? Now, so quick note is that this is essentially the same thing. So this line here does all of those things, all right? And I honestly could have made that spreadsheet even better, but you can make a better version of it when you see what I've done. If not, do however you want. Okay, so let's take a look at the next one. And I'm going to actually calculate this on my spreadsheet over here as opposed to doing it by hand. But I'll leave this up here so that you can see what was done in the previous problem. We're going to do the same thing over here. So if you take a look at my problem, yours might be different. We have a new n, okay, n number of independent trials. We have a new probability for each trial. And remember that on a binomial experiment, the probability is the same for each trial, okay? Kind of like flipping a coin. That's a really good example. You flip a coin, it's either heads or tails. And it's the same probability every time you flip the coin, unless, of course, the coin is, fixed in some way or weighted or whatever it is. But the same probability is 0.5. Every time you flip the coin, it's the same thing. All right, and so then x, you're trying to get x number of successes. So what's the probability if I have 8 trials, the probability of a success is 0.45 on each trial. And if I want 3 successful trials, what's the chance of that happening? That's what we're doing right here. Okay, so let's actually come over here to my spreadsheet. Let's come over to the spreadsheet. And let's take a look here. So I've got x here, okay? And what I'm going to do is I'm going to put in the x value that I have for my problem. My problem is a 3, okay? Now, NCX, this value, I'm going to take right from here, okay? So that value, I'm going to take right from there. So what is that? So if I go and calculate what NCX is, so I typed in my X value. There it is right there. Okay. Then my NCX is what we calculated before. You guys see this? Okay. NCX is what I calculated before. So I need to calculate 8C3. And so for me, 8C3, this NCX part, is 56. And you can just type it in or you can do it on your calculator, figure out the NCX on your calculator, do whatever you want. It doesn't really matter. It's really up to you. Okay? So I've just done that. I let the computer, the spreadsheet, calculate it for me. Okay? Now, or your calculator or that website. It's all up to you. Now, the next thing. P to the power of X. What's my probability? Well, my probability is what? 0.45. So 0.45 to the power of X. And the way that I would go and make this spreadsheet better, this is a really bad version of it. I kind of put it together and kind of haphazardly. And what I should have done is I should have created an NXP column and then had it automatically pull the values from there. It would have made my life so much easier. And you can do that too, but anyways, you get the idea in general. So what do? I take the probability that's given to me, all right, and I'm going to raise it, put it to the power of whatever my X value is. And what I'm doing right there is this step. There it is. So here is 1 and 2 with respect to the original problem we did on the last one, okay? So there it is, and that gives me a value of 0.09 whatever. So that second step is done, all right? And now we move on to that critical third step, that little bit longer one. So here's the third step in our process. And recall that the third step was to take 1 minus P and raise it to the N minus X power. And I noted that right up here, 1 minus P to the power of N minus X. So now we're going to go fill in that formula here. So I'm going to double click this. What is my P? My P for my problem is 0.45. As you can clearly see, this is, again, like I said, a really bad spreadsheet. I should have done things so much differently, but here you go. And I'm going to raise that to, what is my N value in this problem? 8. My N value is 8 minus my X value. This is such a bad spreadsheet, but anyways, the reason why it's not a good spreadsheet is because I have to manually type in so many things, and I really shouldn't have to. What I should do is have an NPX, just like they have here. I just put them in, and then automatically it does everything for me. Try that. Go make it for yourself. And that's a good challenge for you to do all on your own anyways, is to make things better than the way I did it. Okay, so there it is. 1 minus 0.45. 1 minus 0.45 to the power of N, 8, minus X, 3. There it is. So anyways, there you go. I really did not do a good job on this spreadsheet. And so that concludes each of the individual calculations. Now, I went through this and took a really long time because ultimately you could have probably done yours a lot faster. You might already be done with your problem. But I wanted to show you this because it's not going to be just this straightforward. You can clearly see that there's a lot more that's going to happen, and you need to be prepared to probably automate this. With that said, the answer is not the individual pieces. The answer is not these individual pieces. These individual pieces are right here. What is the answer is the product of those. And so see, the product of those is the actual formula calculation. As you can clearly see there, I multiplied all those values from NCX 1, 2, 3 together, and that gives me my probability that we were looking for. So 0.25682, so rounded to 4 decimal places is 0.2568. Okay, there it is. So, look, do you need a spreadsheet to do this? No, you don't. You could have done this exact same process kind of like this problem without any of this so far. You'll see in a moment why the spreadsheet is so kind of handy, but the reality is that you don't need a spreadsheet to do this. I just did it to make my life a little easier. Now, we get to where we start to get a little more complicated. Now, this is where the game starts to change. Okay, this is where the game begins to change with respect to the value and efficiency in maybe automating this a little bit on a spreadsheet. But you, again, can calculate it by hand. Let's take a look at this. So we've got an n, we've got a p, and we've got x. But this time, x successes is an inequality. What does that really mean? That means that you could have not just 3 exact successes, it means that we want, in this case, 3 or fewer successes. In other words, we are opening up our range to what we will accept as a success. Previous problem was like straightforward, we want exactly 3 successes in those whatever trials, number of trials. This time, we are accepting 3, 2, 1, or 0 successes. And here you go. This is where you start to see that coming into play. So the previous problem I did was an exactly scenario. I want exactly 3 successes. That would have been a scenario where you saw x equals 3. But in this case, we don't have that. We contrast that, and we have x is less than or equal to 3. So this less than scenario, that's the one where we are going to attack it next, and let's go take a look at how that's done. Okay, so as you can see in this problem, I've got and how about I move this up just a bit because it's not really necessary for me. I need more room in the other area, okay? So what I want to do here is, oh, I lost my little side. Let me give it back. There. So as you can see here, this looks like it's going to be a less than 3, 2, 1, 0, right? If yours is a 4, you'd be 4, 3, 2, 1, 0. If it was a 5, it'd be 5, 4, 3, 2, 1, 0, and so on. So your less than might not be 3, 2, 1, 0. It all depends on what the inequality is that they give you. With that said, we're going to go substitute and calculate basically this. 3, as if it were the x were 3, 2, as if the x were 2, 1, and 0. Okay, let's go do those individually, and then we'll talk about the probability, which you can guess what we would do with all of these answers. Okay, so let's recap here. This is a much more lengthy problem. It's a lengthy problem because you have to calculate, instead of calculating just one like we did earlier, we have to calculate every single one that is 3 or less because they put the equal sign there. That means less than or equal to 3. So I've got to calculate the probability for 3, for 2, for 1, and for 0. I have to calculate all of those. Now you see what I mean. All right, with that said, let's get to work. So for 3, what is NCX? Well, N is 9 for my problem, X is 3 for my problem, so my NCX is 84. Okay? And there's a couple ways you could do this. You could do all the NCXs and write it down. You could do it that way. You could do all individual pieces. It's up to you, doesn't matter. But I'm going to do each individual one, I'll show you why. Okay? Now, let's calculate the P, the probability of the power of X. What's my probability in this problem? My probability is 0.2. Yours is probably different. So note that my probability is 0.2. 0.2 is my probability. So 0.2 to the power of whatever my X value is. All right? Okay, let's go to the next one. Next one. 1 minus my probability. Well, recall that my probability is 0.2. To the power of my n. What's my n in my problem? My n is 9 minus my x. Let's take a look and verify and make sure everything's correct. Again, you can be doing this all by hand. You can be doing this all by hand. You don't have to do it here. You will see why it is potentially handy to do it here, but it's totally possible to do this by hand and very easy actually. 1 minus, there's a formula, 1 minus my probability, 0.2, see how it's consistent here, to the power of n, my n is 9, I forgot to circle that earlier, minus my x for this one. My x for this one is 3. So there it is. So that's it. And there is the probability for that. If they were asking for exactly 3, if they wanted just x equals 3, exactly 3 successes, that would be my answer that I would submit. But that's not the case. They don't want that. They want less than or equal to 3. So now what we need to do is do the exact same thing for 2, 1, and 0. Now, let me show you finally why it is valuable and helpful to maybe do this via a spreadsheet. What I'm going to do is I'm going to calculate the NCXs for these. Okay, just take a look here. 9C2 is 36. Look at what I did there. So NCX, 9 is still the end. That's overarching through the problem. CX, 2 is the x now, not 3, so I get 36. If you did that in a calculator or on that other website that does it, you get the same answer. Now, 9C1 is 9. And then 9C0 should be 1, you'll see, is 1, okay? Now, watch the shortcut here. I'm going to take whatever my calculation here is, I'm going to drag that calculation down so that I don't have to do all the work all over again. Now notice, let's go to the 2. My x is 2, NCX is 36, p to the x is going to be my probability of 0.2 to the power of 2, which is exactly what it is. What is my next one? Take a look. It sure is consistent with that. 1 minus 0.2 to the power of 9 minus that 2 value, and that's it. And if you go to each of these, you'll see that they automatically change, and I was able to essentially drag, just duplicate everything. So that's it. I mean, bottom line is I just saved some time by dragging the formulas down. Now, again, if you want to just hand do it like this and do 4 of them, you can. It's not that tough. Or, like I said, I built this spreadsheet wrong. I should not have done it this way. I should have had NCX, NPX, NPX, and then it would just automatically pull from whatever I put there. But anyways, it's okay. Now, there are 4 probabilities that are here. 4 of them. The probability for 3 successes, 2 successes, 1 success, or no successes. Everything 3 or less. The answer is not all the individual probabilities. The answer is the sum of those probabilities. Okay? So that's your answer. So my answer for the probability of less than or equal to, or 3 or fewer, 3 or less successes is 0.9144, because I round up. Okay, there it is. Okay, so that's like I said, this homework is involved, and they get a little bit tougher as we go along. Okay, and here's one of them. Okay, this is a very, very involved problem. Let's take a look and let's get right to it. Okay, so this problem's going to take a little bit of time, but if you can do it, it means you have a very good handle on the material. All right, so it says, explain why this is a binomial experiment. Well, let's take a look at the scenario. According to an airline, flights on a certain route are on time 80% of the time. Suppose 10 flights are randomly selected and the number of on-time flights is recorded. Okay, do we have discrete variables? Yes. They're whole numbers, discrete. So that's one of the things. Let's zoom out so I can get all the options here. Well, actually, to make it easier, let's just go through the selections, okay? There are 3 mutually exclusive, possibly, that's odd, outcomes: arriving on time, arriving early, and arriving late. That is not true. That would actually make it false. A binomial experiment, you only have 2 mutually exclusive outcomes. And what are the 2 mutually exclusive outcomes for our problem? On time, not on time. Those are the ones. So this is not the right answer. There are 2 mutually exclusive outcomes: success or failure. There you go, that's better. That is one characteristic of a binomial experiment. Okay, success or failure. Or on time, not on time. The trials are independent. That is a characteristic of a binomial experiment. Are the trials independent? Yes. 10 random flights selected. 10 different airline flights, meaning that in general, these flights should not be connected to each other. They should be independent, meaning that the results from each do not impact the others. That's good. That's a characteristic of a binomial experiment. All right, D, each trial depends on the previous trial. No, that would disqualify it from being a binomial experiment. All right, next one. The experiment is performed a fixed number of times. Yes, absolutely. What is the fixed number of times in my problem? 10. There are 10 times that this experiment is performed to check whether we had an on-time or not on-time flight. The experiment is performed until a desired number of successes is reached. No, that's not the case. That's not the way you do it, because remember that in a binomial experiment, you need to have a fixed number, period. So that contradicts the previous one. You have a fixed number of trials, not an open-ended amount, which is implied by F. G, the probability of success is the same for each trial. Yes. What is the probability of success that's the same for me? 80%, 0.8. Those are the 4 reasons that, or 4 criteria or qualifying standards to make something a binomial experiment. Okay, so there it is. Let's move on. The probability that exactly 6 flights are on time. All right, so here is where we put our work to the test and apply it. Let's write down our N, P, X value, shall we? So we are doing part B right now, and we are going to now tie this all together. This problem, you can do number 12. You have a great understanding of what's going on, okay? So I'm going to erase this. I'm going to get everything all cleared up so that we can work really cleanly through this. I'm going to delete this stuff over here that's unnecessary, and let's get to work. B, what's my N? What is my N? Find and interpret the probability that exactly 6 flights are on time. Well, my N was given to me earlier. There are 10 trials, so the N is 10. Okay, what is my P? My P is what? That was given to me earlier as well, and that was 80%, so 0.8. What is my X? My X is this part right here. That's the number of successes I'm looking for. So in my B problem, or my part B, yours is probably different, I have 10 flights, 10 trials. My probability of a flight being on time is 0.8, 80%. I want to know what is the probability of having 6 on-time flights out of the 10. Our calculation over here is going to tell us. Here we go. My X value is 6. I'm going over to my spreadsheet over here. You can do this by hand. You don't need a spreadsheet necessarily, okay? NCX, 9. Nope. 10 is my N. X, 0. No, my X is 6. So NCX for me is 210. All right? P to the X. What's my probability? My probability is 0.8 to the power of whatever my X is. So 0.8 to the power of 6, which whatever it's right there. There it is. Now, the last one, the third category, or the third part of my formula. 1 minus my probability of 0.8 to the power of N. What's my N? 10 minus my X. Like I said, this spreadsheet is not good. There's so many better ways to do this, design the spreadsheet, and I'd probably redo it down the line. Okay, there you go. But in another sense, it really just, if you go and make it for yourself and you do it better, it will make you understand the work a lot better. So it's a good thing maybe that I did this very poorly on the spreadsheet. Okay, all right, so there it is. NCX, my probability to the power of x, my 1 minus that probability to the power of n minus x, and there is my probability that exactly 6 flights will be on time. 0.088, round to 4 decimal places, 1. And there it is. So, again, just want to drive home the point that you could do this by hand. It's not a big deal. All right? Okay. Now, the other part to part B asks to interpret it. In 100 trials of this experiment, it is expected about how many to result in exactly 6 flights? Well, if the probability is 0.0881, and I do that 100 trials, then all I got to do is multiply 0.0881 by 100. In other words, I'm going to move the decimal place over 2 to the right. So notice how I moved it. If I multiply 0.0881 by 100, it's just essentially moving the decimal point 2 to the right, 8.81. So you ought to pay really close attention to what they're asking for. If you put 8.81, that's not right, because we're kind of thinking about whole number of flights, discrete variables, round to the nearest whole number. 8.81. So that means that we are 9. So in 100 trials of this experiment, we would expect 9 of them to result in exactly 6 flights being on time. All right, let's go to the next part. Here we go. The probability that fewer than 6 flights are on time. Okay, fewer than. What is that? That's another way of saying less than. Now, one thing to think about is the word fewer than, and this can really mess people up. Fewer than, does that mean less than 6 or less than or equal to 6? And the answer is it's less than 6, fewer than 6. So I would not start off by doing 6 here. I would go 5, 4, 3, 2, 1. Okay? I would go 5, 4, 3, 2, 1. And 0, sorry. So I go 5, 4, 3, 2, 1, and 0. Okay, so it's really important that you recognize that. Be very careful. Less than, or equal to, that's going to be including the value. But when they say fewer than, you're going to be just less than. That means you don't include that value. It's less than that. Okay, so here we go. Let's go do our calculation here. My first one, now you see what we're going to have to do here. If we plan things out, I'm going to have to calculate 5, the whole thing for 5 like we did up here. 4, 3, 2, 1, 0. Then I'm going to add up all these values. Okay, here we go. NCX. Well, I guess I probably need to write this down. What's my N? Well, my N, how about I erase this so that we don't have any confusion. We're now on to C. Okay, my N is still 10. What is my P? My P is still 0.8. Now, what is my X? My X is going to change depending on which part of this I'm doing. So I've got to do a 5, a 4, a 3, a 2, a 1, and a 0 scenario for all of this. And that's what you see over there. So we're going to go handle the 5, 1 first. What is my N? It's 10. Yours is different. What's my X for this first one? It's a 5. So 252. I'm going to do this is I'm going to calculate all of my NCXs for all the pieces. So now I'm going to go do 4, which is 210. I'm going to go do 3, which is 120. I'm going to go do 2, which is 45. 1 should be taking me back to 10. Yeah, and then 0 is always 1, and you can test it out. It's always 1. So what did I just do? I saved myself some time, kind of stayed in the same train of thought, and did all of these. Okay, I did all of my NCXs for all 6 numbers from 5 and under, fewer than 6. Okay, because you gotta count 0. And this is one that could really mess people up. I didn't put as much emphasis on this as I should have, but make sure you remember to calculate 0. You miss 0, you are going to miss a big, big piece. You will get it wrong, okay? So make sure you get 0 in there. So less than or less than or equal to, that's going to depend on the problem. In our problem, it's a less than. Okay, what do I need to do next? So I've got the NCX, now I've got to do the p to the power of x. What is my p in my problem? My p is 0.8. 0.8, oops, 0.8 is my exponent, is my probability, all right? And now what I'm going to do is, to save myself time, I'm going to just drag this all the way down. So notice how I just basically got all of that same formula to do all of them for me. Okay, there it is. Now let's go to do the last one. 1 minus my probability. My probability is 0.8. To the power of, what's my n? My n is 10. Okay, my n is 10. What is my c value, my x value? It's there. It's 5. It automatically pulls it from over there. Okay, so that's correct. Automatically takes it from whatever was over here on this column. And so there's the calculation. If I just take that and drag it down, it's going to tell me everything. And then what I should do is I need to pull all this down so that it recalculates all of the probabilities. So all the products, the full multiplication. So what I did here is, we know that this final column is the important one where it multiplies NCX, p to the x, and 1 minus p to the n minus x together. Notice how it does that. Notice how it does that. All the way down, does it all the way down. Now, are those individual ones my answers? Of course not. My answers are the sum, or my answer is the sum of all of those individual probabilities. So my answer is that right there. So it's 0.0328. Okay? How did I get 0.0328? Because this is 0.03279 rounded up. And we round to 4 decimal places. What's the big takeaway? Oh, probably a few. Number 1, fewer than means less than, not less than or equal to. Number 2, make sure you count it down to 0. Number 3, execute the formula properly in whatever way you like, manually doing individual or working with it on a spreadsheet. Okay? Be sure to get all the individual pieces correct, probabilities and so on. And then you need to add together all of your probabilities to obtain the actual answer of the total probability. Okay, they're going to ask you again, in 100 trials of this experiment, is it expected that how many will result in fewer than 6 flights? Well, just like we did before, you're going to take your probability and multiply it by whatever number of trials that they throw at you. Like this could be 99, 112. It's just, mine happens to be a nice round number because they're just going to make our lives, or my life at least, a little bit easier. So all I got to do is 0.0328 times 100, which is essentially moving the decimal place 2 to the right. So that's going to be what? 3.28. But what did they say? Round to the nearest whole number because we're dealing with discrete variables. 3.28, that's just a 3. Okay? There you go. All right. Let's go to the next one. So the next one is at least 6 flights. Okay, at least 6. That changes the game. That changes the game, both from an English standpoint and from a calculation standpoint once you figure that part out. So we are now on to part D, at least 6. So the question is, for at least, is it greater than 6, or is it greater than or equal to 6? Which one of those is that English language describing? What is that language describing in this case? probability that at least 6 flights are on time. Well, that means that you get to have the 6, at least 6. The minimum is 6. This is what you're driving at. That's the inequality that you would derive from that. So in the at least scenario, you're looking at either a greater than or equal to, depending on the language that's being used. So if we come back and get things set up, my n is still 10, my p is still 0.8, my x is now 6, 7, 8, 9. Where do I stop? I stop up to the max. What's the max that it could be? 10, whatever my n value is. This is a very important number. It's the other end of it. Like 0 was important in the fewer than scenario or less than scenario. Whatever your n value is, that's where you would stop when you're dealing with the at least scenario. So for me, I stop at 10 because if I have 10 flights in my trials, I can't have 11 that are on time. The max I can have is all 10 being on time. So be aware of that, okay? So with that said, let's go take a look at and do this at least part, okay? All right, so I'm gonna clean things up here and let's take a look. I'm gonna, where do I need to go? I need to have a 6, 7, 8, 9, and 10. I'm gonna move this between elsewhere. Okay, I'm just gonna move it over here, okay? Put my line back over there. Okay, so I need to have a 6, 7, 8, 9, and 10. And what I probably should do is move this down so it's not messing with your eyes, okay? So I've got to do the at least scenario, and in my at least scenario, I've got to get 6, 7, 8, 9, and 10. All right? Those have to be individually calculated, like we did before, and then all the probabilities need to be summed and added together. Well, here we go. What's my n? 10. What's my first x? 6. So I actually have that already, don't I? It's over here, but whatever. I'll just redo it, right? 210. What is my p to the x? My p to the x is, well, I've got, what's my probability? It's 0.8 to the power of my x. That's good. That looks nice. What's my 1 minus p? 1 minus the probability, which is 0.8. So my probability is 0.8 to the power of 10 minus 6. There it is. And so now I need to multiply my NCX, my p to the x, and my 1 minus p to the n minus x, and there's my first probability. And now all I gotta do is do the same thing for all the others. Ready, here we go. So I'm gonna go calculate the rest of the NCXs. So 10C7 is 120. 10C8 is 45. 10C9, 10. And 10C10, you'll see what it is, it's always 1. Okay? Now, if I just drag this down, because I already calculated everything, there it is. I drag this down, and it just so happened all my formulas were good. And then I'm going to just drag this down just in case, and those are all good. So, in other words, what do I got there? I got all of my probabilities, individual probabilities for 6, 7, 8, 9, 10 successes. The probability of getting at least 6 successes is going to be the sum of all of those. And that would be our answer, 0.9672. Hopefully that's right, 0.9672. All right, there it is. So I went through that one a little bit faster, but the reality is that it's the same thing, just a different group of probabilities that had to be selected and summed, okay? So there it is, let's move on, and they're gonna ask you again the 100 trials, multiply as necessary depending on your scenario. That gives me 96.72, or in other words, 97 out of the 100 flights will probably be where we'll have at least 6 being on time, or 97 times where I calculate this trial of 10 flights. Okay, so now The probability that between 4 and 6 flights. Okay, so we finally get to the last part. Like I said, this is a long problem, okay? A very, very long problem. But the main reason why this is a long problem is because there's so much explanation on the details of it, okay? I do want to note, remember the 10, just like we remember the 0, I grabbed the black marker. Okay, so the probability that between 4 and 6, here it is, here's the last part of this problem, between 4 and 6, inclusive, are on time. So what we have here is we need to go set up our problem. Is the n the same? Yes. Is the p the same? Yes. What would be my x? Between 4 and 6 means that you get to have, and I'll say between 4 and 6, the question would be, is it 4 less than x less than 6, where we don't include the 4 and 6? Or is it 4 less than or equal to x less than or equal to 6, where we do get to include the 4 and the 6? And I already kind of alluded to it a moment ago. Yes, it's that. All right, so that means I need to calculate the probability for 4, 5, and 6. Well, the great thing here is what? All the work I did earlier, all of the work that I did earlier, all of that work, it actually got me set up where I can answer this problem pretty quickly. Because all I have to do is figure out what's the probability for 4. Do I already have that? I do. There it is. Probability for 5. Do I have that? I do. Probability for 6. Do I have that? I do. They're all right there. So what do I need to do with those? I need to add them together. So if I just come down here, I'll hit the equal 4 plus 5 plus 6. Those 3 probabilities are, for me, my problem, what they're looking for when we're doing the between case. And so there it is, 0.0323, hopefully is the correct answer, 0.0323, and oh boy, hold on. Four, 5, 6, let's see here. Oh, you know what? That was the wrong problem. I should not have taken it. I think that was the previous problem. That was wrong. This was from the previous one. I think. Yes, it is. So I actually pulled the wrong one. Yep, it's wrong. Wrong 6. I should have taken it from here, not up there. That was not, this was not, that was from the previous problem. That was a big mistake. Make sure you clear out your data. Sorry. So I need to cut off that last one and replace it with this one. Sorry, you see the mistake there? Okay, so that was from a previous problem, wasn't paying attention. 4, 5, and 6 from this problem are right there. Not paying attention. There it is, 0.1200. Let's hope that is correct, okay? All right, there you go. All right, so, and maybe they'll ask us one more. Yes, again, if you had 100 trials, what would happen? 12 would be between there. Just multiply by 100 and round accordingly. And there it is, one of the most difficult problems. This is a lot. There's a lot going on here. If you can do it, you have a great understanding of what's going on. Okay? What I want to do is I'm going to leave, well, actually, we actually need to do number 13, so let's go after it. Let's take a look here. Okay, so basically almost everything that I've taught you has been done, okay? And so this next part, I'm moving down this side because we're doing something similar. You've seen it before, but I just created another table for it. And so let's take a look here. According to a study done by a university student, the probability of a randomly selected individual will not cover his or her mouth when sneezing is 0.267. That's important because what is it? That is our P. That's our P. Note it. Suppose you sit on a bench in a mall and observe people's habits as they sneeze. Here we go, part A. What is the probability that among 18 randomly observed individuals? Oh, stop right there. 18 individuals. What's that? That is your N. Exactly 6. Exactly 6. Here we go. That's the kind of stuff that we've been talking about. Exactly 6. What is that? Your X. And now I have the information to go do the first part. That's just a straight up calculation for one of them. And I'm going to come over here. I'm going to just save this line right here. And, well, how about I do it on this first one? It's okay. I'll use this first one. 6. Okay? So if I have X is 6, now I got to do my NCX. So what is my N? My N is 18. My X is 6. So my NCX is 18,564. Okay? I got that from right up here. You get it however you want. Okay? So 18,564 is my NCX. Now I need to do 1 minus P to the power of X. What's my probability? 0.267. So my probability in my problem is 0.267. Yours might be different, but there's the calculation. 1 minus 0.267, just like we've been doing, to the power of whatever your X value is. There it is. Okay? And then finally, the last part, 1 minus, and here's where it gets tricky. In your notes, there is something that says number 13 in your notes. Fewer than, fewer than, fewer than. This is actually related to the last problem. Sorry, this is for C. I can't use the same table for this. So I'm going to back up here. I need to back up here. Hold on. I'm going to use this one. Sorry. So 6, I'm going to put it right here. So 6 is my X. Let me start over again. NCX. So my NCX is 18,564. Now my P to the X is my probability of 0.267. And then my 1 minus P is 1 minus 0.267 to the power of 10 minus my X. Okay? And I need to actually, whoops. I think I actually just closed out my homework. I'm going to have to pull my homework up again. One moment. Oh, there it is. Okay, let's restart this. Okay, so I kind of had a little detour there because this table, sorry, is for part C. So I'll deal with that later. Part A is a standard problem, sorry. It is a standard problem, and I'll talk about, you'll see in a moment why that table is not appropriate for A and B. All right, so my X is 6 for part A. My NCX is 18,564. I calculated it right here, 18C6. Then my P to the X, my exponent is 0.267 to the power of my X. Then my 1 minus the 0.267 to the power of 10. Oh, nope, that's not right. My N is not 10 in this case, it's 18. Okay, be careful. So you guys are probably not making these mistakes, but I'm just kind of all over the place because I was reusing formulas. And there you go. There's my probability. Okay, so my probability is 0.1618. All right? This is straightforward. This is just like the very first one that we ever did, starting with our calculations. All right, let's move on. B. Okay, so B, let's take a look here. For B, it says, what is the probability that among 18 randomly observed individuals, N is 18, fewer than 3. Oh, there it is again, our favorite fewer than. So fewer than 3. That means our X. Fewer than means what? Not equal to, it means 2, 1, and remember the all-important, 0. So in order to do that calculation, we've got to do 2, 1, 0, and add all those together. So I'm going to come over here, And take a look at what I've got here. I don't need 5, 4, and 3 here. I'm just going to delete these out. I've got 2, 1, and 0 that I need to calculate. I'm just trying to save some time. You can do things differently. And now we've got to do our calculation. I've got to redo all this and all of this for my particular problem. But that just saved me a little bit of time. 2, 1, 0. Okay, let's do the NCX's first. What's my n in my problem? 18. What's my x? 2. So my NCX is 153. Let's do the next one. 1. NCX is 18. And then of course this one should be a 1, which it is, and there's the 1. So I just calculated all of my NCX's for my part B. Now I need to calculate my p to the x. What's my probability? 0.267 to my x value, which is there. And I'm going to drag that down so I don't have to retype anything. Then I'm going to come over here. 1 minus my probability of 0.267 to the power of my n, which is 18, minus my x. Notice what I did there. So 1 minus, just like we've been doing, my probability of 0.267 to the power of my n, 18, minus that x value, and that's it. And so that will calculate my probability, and I need to drag this down so I can save some time. And there are my 3 probabilities. What do I need to do with those? Add them together. So the sum of those, that's my answer, and I need to round that to 4 decimal places. 0.1039. Okay, and there it is. So the first 2 parts are very straightforward, super straightforward, stuff that we've done in the previous problems. Now the last part is the tricky part. The last part is the new part. The last part is the stuff that messes people up. So, and I made a specific note about that in your notes, and that note is for fewer than, okay? So fewer than, this is where it comes into play. So in my table here, this part right here is the part that is related to the fewer than, okay? I'm going to change some things because I kind of messed it up earlier. Let's take a look. Would you be surprised if after observing 18 individuals, okay, n is still 18, p is still 0.267, fewer than half covered their mouth when sneezing? Fewer than half. Fewer than half. What does fewer than half mean? Well, we know that fewer than means less than. And then half is half of whatever you have here. What's half of your total number of people, your n? 9. So in other words, for my problem, they're really asking you, would you be surprised if after observing 18 individuals, less than 9, in other words, 8, 7, 6, 5, 4, 3, 2, 1, 0, all those scenarios cover their mouths when sneezing. That's what they're asking here. And so what we have to do is calculate all of that. But there is one very important twist to this problem which makes it very difficult and easy to make a mistake. And there's a note specifically in your notes on it, a bullet point. It says number 13, fewer than. You're going to substitute 1 minus p into the formula for p rather than the given p like we normally substitute. Let me explain what's going on here, okay? So let's first and foremost calculate the NCX's for all of that. Then I'm going to go to that note. So NCX, what's the NCX? Well, I've got 18, C, and I got to start at 8, right? 43, 758, okay? Then I got to go 18C7, 31,824, 18C6, 18,564, and I had all these pre-done. 18C5, 8568, 18C4, 3060, 18C3, 816, 18C2, 153, 18C1, 18, and of course this last one's going to be a 1. So I did all of those right away, so I don't have to keep going back and forth. I can kind of keep my train of thought in the same concept. All right, now this next column is the one that's tricky. What did I say there? I said substitute your 1 1 minus p for that piece. So normally, what would happen here? Normally, the formula would be p to the x. What is this normally? This normally is p to the x, right? That's the way we've been doing it all class long. But what happened here? We need to substitute 1 minus p for that. What is this normally? Well, I'll talk about that in a moment. So instead of just taking your p value, you need to put in whatever 1 minus p is. Now, you can do that ahead of time if you want. So if you want to do that ahead of time, you certainly can. So for this last part, your p value is actually going to be 1 minus, in my case, 0.267. And that's where you get that there. And so if you do that ahead of time, like for my problem, that would be 0.733, I believe. Okay? So you need to put that value into there instead of the 0.267. And what does that come back to? That comes back to stuff we talked about before. 1 minus the probability is the other side of it for the, for fewer than half, but the surprising stuff. That's the trick. It's so tricky. So there it is. I already calculated. I did it. I wrote it in for you. So you're not going to see 0.733 there because it's going to calculate because I want to show you that. So in other words, you just take the opposite probability. Whatever the probability is that they give you, get the opposite and put it into that formula. Or run the formula as 1 minus whatever your probability is. Okay? And so there it is. I'm going to drag that all the way down. And there it is. Okay. Now the same thing is true for the last part, that other part. So there's the formula. Look at what I did there. So normally what is this? It's 1 minus p to the power of n minus x. That's what it normally is. But instead of just being p, we substitute whatever 1 minus p is. 1 minus p in my case is 0.733. But I just wrote it in there as 1 minus 0.267 in my formula. So it doesn't really matter how you want to do that, but just make sure you're taking the opposite probability. Not the 0.267, but the opposite side of it to go into that value. If you automatically subtract it earlier, then you can just use these original numbers. But if you don't automatically subtract it, you got to do the subtraction in there to make sure you don't use the other one. Okay? And then I'm going to save time and drag it all the way down so it calculates for me. Now you guys see why I wanted you to maybe potentially use a spreadsheet, because it could save you the time. And of course, at the end, the product of all of those products added up, that is the answer. So now, the probability is what? I'm going to come over here. It's 0.0089. That's my probability. Now, here's the deal. How do we interpret this? If your value here is less than 0.05, and I noted it on the notes, the event would be surprising and unusual, just like we've been talking all through the semester. Is it less than 0.05? Yeah, it's significantly less than that. Here's 0.05 right here. It's much smaller than that. So it would be surprising because the probability of observing fewer than half is 0.0089, much smaller than 0.05, which is an unusual event. This is a hard problem in its own right. Okay? All right, we got one more problem to go. 15 and 16 you can do on your own. Your notes explain them. They're just little definition problems. I'll just leave those for you to do all by yourself. But here we go. This is our very last problem. Number 14, it's not too bad, but and to do it, we use this last part to help you get it done. Again, like I said, it's not a big deal, but especially compared to what we've done so far. The previous stuff was brutal. It's a lot of work. Okay, according to a report, 79.3% of murders are committed with a firearm. If 100 murders, we're doing part A here, if 100 murders are randomly selected, how many would we expect to be committed with a firearm? Okay, so this is super easy. Given what we just came from, this is really easy. All you have to do to know that is you already know the probability. There's your probability p, 0.793. So of course you want to convert that to a decimal. So your probability is 0.793. And if you have 100 murders, there's your n value, right? There's your n value. So all I have to do there, if I want to know what would we expect, just like we did in previous problems, if we already know the probability, we have a certain number of n target, all we got to do is, I'm going to come over my spreadsheet because I want to just show you here. What's my n? 100. What's my probability? Well, mine's 0.793. So my expectation would be I would have 79.3 of those 100 murders to be committed with a firearm. It's very straightforward. That's it. So in other words, all that to say, to complete part A and to figure out your expectation, multiply your n by your p. Straightforward, and there's mine right there. Okay? So, and this is a very important value. I'm just going to highlight it so that you'll see it, so because we're going to come back to it later. And B, the second part of this. Okay, in part B, it says, would it be unusual to observe 89 murders by firearm in a random sample of 100 murders? And why? All right, so in order to answer this question of whether it's unusual or not, you have to go do this part over here. And I just wanted to save time and show you the calculation pre-done because I knew this lecture was going to be super long. So in order to answer B here, this part gave you part A. Okay, that was part A. Now to answer, I just kind of got my stuff in the way. Hold on, let me rewrite that. So this right here is part A, okay? And so B is this right here, all this down here. Step 1 in part B, you have to calculate 1 minus P. Whatever your P is. Now we get the opposite. So 1 minus P. So what is my 1 minus P? Well, my probability is 0.793. So 0.793 is my probability. So 1 minus that is going to be my answer for that. Okay? Which is 0.207. After you do that, what you need to do is you need to calculate NP, which is your mean. We already did that right here. So your N times your P, which we already did. In other words, your mean times what we just got here, or your 1 minus P. So that's why you see in step 2, NP times 1 minus P. Well, NP, we found it out, or you can just multiply NP, 1 minus P, and you get the answer. There's the 1 minus P. Okay, good. There's that, okay? And then what you're going to do is you need to take the square root of whatever you got right there. And that's why I use the square root SQRT function. And you can do that on all this you can do in your calculator. You don't need a spreadsheet, but the thing is that it's a little bit, this was easier for me to set up this way because so much of this class was done on a spreadsheet. I didn't want to be pulling up windows left and right. So that's the square root, okay? What does that represent? And in your notes, you will see that. The square root, that answer right here, part 3, this is your standard deviation. So while this right here was your mean, that answer right there is your standard deviation. And what we're doing here is we're trying to figure out if this is normally distributed and we have a mean mu, then within 2 standard deviations, 1 SD, 2 SDs, 2 standard deviations. In other words, and they use our sigma symbol here. So within 2, right? That's what they're saying. 2 standard deviations. Does this value, 79.3, fall within there? Well, you first have to figure out what is a standard deviation, like we know. Well, all that we did just now is to figure out how much 1 standard deviation is from our mean. So up 4.05, down 4.05. up another 4.05, down another 4.05. And so this bottom part tells me my range. So what is this value? It is my mean minus 2 standard deviations. So that value here is my mean, 79.3, minus 2 of these, which takes me down to 71.20 if I round to 2 decimal places. That's 2 standard deviations. Now the other side of it is my mean, plus 2 standard deviations. There's my mean right here, 79.3, plus 2 standard deviations. So what is that value for me? And you can all do this by hand. It's not a hard thing. You do this on your calculator, 87.40. So 2 standard deviations with a standard deviation of 4.05 down is 71.2. 2 standard deviations up is 87.40. And the magic question, the important question does 79.3 fall within that? Does 79.3 fall within, oh, sorry, not 79.3. Wrong. 89. 79.3 is your mean. Of course it falls in there. Duh. So, does 89 fall within that? Your number might fall within it. Yours might not. It depends. Does mine? No. 89 is outside over here for me. 89 is outside. But if your number, say, for my problem was 75, I'd be good. If it was 86, I'd be good. If it was 72, I'd be good. But it's not. My problem is 89 and out. No, because 89 is greater than. No, because 89 is greater than my mean plus 2 standard deviations or 2 standard deviations above my mean. Select the correct one. If it were correct, if it was good, if my number fell between, I'd say yes, because 89 is between these two things. 2 standard down, 2 standard deviations up. You just gotta find the correct one that applies to yours. Oh boy, did I calculate mine wrong? Let me see here. Mean plus 2 standard deviations. Mean minus 2 standard deviations. Oh, sorry. Unusual, I apologize. Unusual means that it falls outside. That's what we said. This is unusual territory. Oh, sorry, not paying attention. Regular territory, not unusual, is when it falls in between. Sorry. Unusual is when it falls outside. So 89 is outside. So therefore, yes, it would be unusual because 89 is greater than 2 standard deviations. Now, if your number fell in between, you would say, no, it's not unusual because 89 is between those. Sorry. Totally messed that up. I apologize. That should be the right answer, and it is. Okay? That's it. You can do 15 and 16 all by yourself. They're just definitions, and those are in your notes at the very end.